Welcome to the second part of my lecture on the NumPy array. In the first part of this lecture, we had met the array. We had learned about its various attributes. We had also learned how to create a NumPy array using the array function from the NumPy module. In this lecture, we are going to take a look at some other more detailed things that are available with the NumPy array. So first, we will of course have to start by invoking the mantra that's our starting point. We have to import NumPy, and as we explained in the previous video, we will always import NumPy as np. Then we will import matplotlib.pyplot as plt. As I explained before, this second part is not essential to deal with the NumPy array. However, if you want a nice visual way of seeing the results, plotting them using the matplotlib library can be very useful. Now, in the first part, what we have seen is how to create a NumPy array. We had also seen its basic properties, and we had met the np.array function, which creates NumPy arrays for us. We will first look in this lecture at some other functions that are available which makes creation of special arrays easy. We will first take a look at some methods which will allow us to create new arrays which are filled with constants. Very often we need an initialization where we need an array which is full of zeros. Now, because this is a very common need, NumPy actually allows you to do this directly using a function provided by it. This function is called, as you can guess, zeros. So if I say a equals np.zeros, and that's a function, so I have to give an argument in the bracket. Let's say I give the number 10. So this returns for me an array which has 10 zeros in it. So the 10 that I have provided here as an argument is really nothing but the size of the array that I want to create. Actually, I can do something else. Instead of giving a single number, here I can actually give a tuple of numbers. In this case, I am giving only 2, and you can easily guess what this will do. This will produce an array which has zeros in it, but one which has 3 elements along axis 0 and 4 elements along axis 1, which to us is a 3 by 4 matrix. So let's take a look. Right, this is a 3 by 4 matrix filled with zeros. Now, if I wanted to know exactly what other arguments I can give np.zeros, I can of course look up a text, or it's perhaps much easier to just ask Python itself. Python has a wonderful help system which you can invoke by using the help function, and NumPy actually has a better documentation than most Python modules. So let's just take a look. Just ask for help on np.zeros. What Python does is returns to me the inbuilt help. So here it is telling me the zeros is a function. It's a built-in function. And what it takes is one argument. The first argument is shape. Then it has another argument, dtype equals float, and order equals C within quotes. Notice that both the dtype and the order are arguments for which default values have been given. So you actually need to provide at least one argument, the shape. You are told here the shape is either an int or a tuple of ints. So it essentially asks for the shape of the new array. So it's a tuple or a single number. If you give a tuple, it's going to give an n-dimensional array. If you give a single number, it returns a one-dimensional array of that type. The second argument, which is optional because its default value is given to a float, is dtype. So, as you saw in our examples, both the arrays that we created came out to have 0 point as elements. That's of course a floating point number 0. But I can actually set other data types. And finally, you also have one more argument, which is the order. This essentially has to deal with how the numbers are to be stored in the memory. Unless you are really going in for very high-end programming, you don't really need to bother too much about this argument. The Numpy docstring here actually has much more information. It also tells you that it returns an output, which is an n-dimensional array of zeros with the given shape, dtype and order. And it also tells you that in addition there are some more similar functions like zeros like, empty, ones, full, and it also gives you some examples. These are the kind of examples that I have been giving you. So let's just see one more example of zeros in action, and for that I will get out of the help first. You have to type Q to do that. Now let's repeat this, but this time I will give a dtype. Let's say of int. So what that will do is will produce a 3x4 array again filled with zeros, but this time every one of the zeros will be integers. So as you see, the difference between this one and this one is apparent. Here all the entries are integers because you have specified the dtype to be int. So that's more or less all that I have to say about zeros, but as the help told us, there are some more functions like this. For example, you have ones. So np.ones essentially again takes in a tuple or a single integer as argument. Let's say I give 2,5 or 2,6, and just for the heck of it, I give dtype equal to complex. And let's see what I will get. I will get a 2x6 array filled with ones now, but the number will be 1 point plus 0j. Right? Because I've specified the dtype to be complex. In addition to this, I might want to fill up the array not with either ones or zeros, but with some number of my choice. So we have a function called full in the Numpy module. Now I don't really remember exactly what the arguments are that we have to supply to the function full, but that's easily remembered. All you have to do is type out the help. So you will get to know exactly what to supply. The full function. Notice here it says full. After that, shape is the first argument. Fill value is the second argument. These two arguments don't have default values assigned to them. Dtype is by default none, which means in this case whatever fill value you give decides what the dtype is going to be. The order once again is a C-type order by default, and what it does is returns a new array of the given shape and type filled with the fill value. So with this help, let us try to figure out what I will get to use the full. So the shape comes first, so that is either an integer, in which case you get a one-dimensional array, or a tuple. Just for the heck of it, let's give 3 numbers in the tuple. So this is a 3-dimensional array. And then I have to give the fill value, whatever I want to fill it with. 2.5. Let's see what A is now. Okay, in fact A is quite big. It is called off the screen. This is what it looks like. In fact, if you look at it, this has shape 3, 4, 5, you basically have 3, 4, 5 arrays. Which you get when you move along the 0 axis, this one, then this one, and then finally this one. And within each array, if you move along the 1 axis, which is when you go down in each array, you have 4 elements, and lastly you have 5 elements when you go across. So this is a 3, 4, 5 array, and it has been filled with 2.5. Of course, if you check the dtype of this array, it's float 64. This dtype has been taken from the fill value. But you can actually override that. You could actually say and of course there will be a conflict here. You're giving a fill value which is a float and you're specifying a dtype which is int. So in this case, what Python will do is convert the supplied fill value to an int and push that in a 3, 4, 5 array. So let's check whether that's really what has been done. If that is exactly what has been done, now you have a 3, 4, 5 array, a 3-dimensional array. Just to verify it, that check that end in S3, and each and every element of this array has been filled, not with the fill value 2.5, but what you get when you try to cast 2.5 into an integer. So we have seen np.zeros, we have seen np.ones, we have now seen np.full. We also have an np.empty, let's say 4. This will give me a 4-dimensional uninitialized array. So now if you look at A, there's some values, pretty small values. In fact, they'll all look pretty close to what you would expect if you tried to get a floating point 0. But that's not really guaranteed. The values you have here depend strongly on which particular version of the OS you're using or the interpreter you're using, because in principle you could have just 4 random values in these size because you have not initialized anything. But by default the empty array is produced with a dtype of float. So after this you can actually assign elements to it. So like say A1 would be 2. Now notice if I'm giving an integer, but it will take it in a float. So now check what A is. The 0th element has been changed to 1.2 and the 1th element has been changed to 2, as I've said, but it is a floating point 2. The 2th and the 3rd elements have not changed, they're still stuck at 0 or something very close to 0. In addition to these basic functions that produces arrays filled with constants, or as in the last case an empty array, you actually have versions of these which produce arrays like a given array. To understand what that is, let's first create an array using our old friend the array command. Let's say this of course is a 3x2 array, and this 3x2 array has elements given by 1, 2, 3, 4 and 5, 6. This is an array which with shape, as I've just said, 3, 2, and a D type, of course, of int. Just remember, when we create an array filled with zeros using the np.zeros, by default the array is produced with floating point numbers. Just to remind you of that, let me just show you what np.zeros will do. It will produce a one-dimensional array with 2 elements, each a 0. Now, let's try the zeros like function. So I have an array A which has shape 3, 2 and its D type is int64. And now let's try. So this is a different function from zeros. It's zeros like, and I have to give an argument. As an argument, I have to give a pre-existing array. So what does it do? It now produces an array filled with zeros, but it's an array with the same shape. Remember, it's like, same shape as A, also the same D type as A, so all the elements are integers. Similarly, I have a ones like, I have a full like, which will take 2 arguments, the A and the fill value. Notice that despite the fact that I've tried to push in 2.7, Python truncates that and puts only 2 as elements, because remember, A has D type int, and when you're using full like, you're going to produce an array which is like A in shape and D type, to also have an empty like. We will now take a look at some Numpy functions which are designed to produce matrices. And one of the most obvious and important matrix that we will need is the identity matrix. And to produce the identity matrix, Numpy gives us a function which is rather obviously named identity. So if I type out np.identity, and I need to give it an argument, the obvious argument here is just the size of the identity matrix. So if I give np.identity 4, I get a 4 by 4 array, an array with a shape 4, 4, which of course is an obvious stand-in for the identity matrix, a 4 by 4 identity matrix. Now there is another function which is rather similar that's available in Numpy. It's called I. Well, actually the name I, E-Y-E, is a play on the sound of the letter I, which stands for identity. And if I just say np.i4, I will see no difference whatsoever. I will see exactly the same result as np.identity. So why do we have a different function at all? Well, I actually is more versatile. It produces not only the identity matrix, but it produces things close to the identity matrix in this sense. It has one more argument called the shift. It's called k. It's a named variable. I say k equals followed by the value I want to give it. In this case, let's give it 1 and see what happens. You see, you get a matrix or an array which stands in for a matrix, which looks almost exactly like what we had before, but now the ones have been shifted upwards from the diagonal by 1 unit. So k is the amount of shift which you have. So if you use k equals 3, for example, here, the ones will shift all the way up to the top corner so that you will end up with a matrix which is almost a null matrix. It's only a single one. If I use a bigger k than the size permits, I will end up with a null matrix. Of course, I could just as well use a negative value of k, which would shift the non-zero diagonal or non-zero semi-diagonal down. So -2 moves it 2 spaces, so 0 would have been right down the diagonal here, Minus 1 would have been here, minus 2 is here. There is another special kind of matrix that we often need to create, which is a diagonal matrix. So for this, again, Numpy gives us a very simple function. It's called np.diag. And what it takes is not a number, but a list. A list of entries, or could even be an array, which has the diagonal elements that you want. So in this case, I'm giving my np.diag function an argument which is a 5-element list, and I will end up with a diagonal matrix with elements 1, 2, 3, 6 and 8, exactly what I specified in my list. And notice that because I have given a list which has integers only, the resulting array has a d type, which is int. Even if I had changed a single one of them to a floating point, the resulting array would have been an array of floats. By the way, in identity and I, as you have noticed before, by default the d type is float, as is evident here, but I can actually type in the value of d type, like say int, and now I'm going to get a shifted identity matrix, shifted by 2 steps down, but with only integer elements. Let us now come to 2 functions which are going to be extremely useful in all your applications for Numpy with Numpy arrays. There are again ways of creating Numpy arrays, but these are going to be extremely important. So one of them is a sort of successor to the familiar range function from elementary Python. Just to remind you, in Python, the range function is a built-in function which produces a list with the number of elements specified. Say for example, if you say range 3, it produces 3-element list with elements 0, 1 and 2. So this is basically a list which has the indices which you will get for a list of size 3. One word of warning here, I'm using Python 2.7. In Python 3, the range function no longer produces a list. It actually produces something called an iterator, from which you can create a list. So if you were using Python 3, you would see exactly the same thing that I would if you use this. Change the range 3, which in Python 3 point whatever is an iterator, into a list. Of course, here range 3 is already a list, so whether I do this or not, I end up with the same result. Now, range can take up to 3 arguments. So if I give it 2 arguments, the first argument now is where the listing is supposed to begin. And notice that although we call the second argument the stop, it doesn't really stop there, it stops one short. So range 3, 10 is 3, 4, 5, 6, 7, 8, 9. I can actually also give a step, so it is go from 3 up to or just short of 10 in steps of 2. So it's 3, 5, 7, 9, a list in this case. One thing you cannot do in range is give a floating point input. So although you might be tempted to think that this will produce 3, 3.2, 3.4 and so on, it will not. As you can see, you are getting a type error here. It's saying range integer step argument expected got float. In fact, in the range function, all the arguments have to be integers. Now, very often we need to produce equally spaced arrays of numbers, just like here, but I would perhaps often want the arrays to have fractional or floating point starting points, ending points, or floating point intervals. And for this, the range function is not adequate. You can create the range list and then use things like list comprehension, as you must have learned in elementary Python, to get to whatever list you want. But in Numpy, the need for such equally spaced arrays is so common that Numpy has given you a new function to do this. And its name is arange. So it's pretty close to the original function as far as name is concerned. However, let's see what it can do. If I give it the same set of arguments, 3, 10, 2 as before, it produces exactly the same. Well, not exactly the same thing, because this is an array instead of a list, but it's an array consisting of exactly the same numbers that you had in the list before. But now, notice what you can do. You can produce a range which goes like this. So now you'll have elements like 3.1, then 3.1 plus 2 points, and that's 5.8, then 8.5. If you tried adding 2.7 to that, that would have gone beyond 10.5. So you stop. So arange, of course, produces a much more versatile array of numbers than range does. And of course, the other advantage is that it produces an array which you can use in many other ways, as we have already seen. So let me just take a quick look at the help of the arange function and see whether there are certain other things that I've forgotten to talk to you about. Well, not really much. It says start value, which is optional, a stop value, which you have to give, and a step, which again is optional. These things in square brackets are optionals. D-type is none. That means the D-type is actually produced via what kind of inputs you give it. And it says returns evenly spaced values within a given interval. Of course, it goes along and says a lot more things, gives you a lot of detail about this, gives you some examples. So you can always take a look at the help to figure out more about this. There is another function which Numpy gives you, which produces something similar, but now instead of specifying the starting value, the ending value, and the step size, what you do is this. The function's name is Linspace, for linear equally spaced, and for this you give the starting value, the ending value, and the number of terms. So the third entry here for Linspace is not the step, but it is the number of terms you want. And in this case, as you can notice, by default Linspace returns both endpoints. So when you say 3, 10 is produces an array starting at 3, ending at 10, it has 10 entries, which means it has 9 intervals, and this is why your gap is actually 10 minus 3, 7 divided by 9, 0.777 recurring. And so this is what you end up with. The Linspace actually takes more arguments. So you must give it at least the beginning value and the ending value, without which it will not be able to work. If you do not give it the number of elements, it can still function, because in its definition there is a default value for the number of elements, happens to be 50. So if you do not specify how many elements you want, you are going to end up with 50 element array. So here 50 elements starting at 3, ending at 10, 49 intervals. So this gap here is actually 7 divided by 49, or 1 by 7. Now, in addition to these, there are 2 more arguments that you can give. Notice that unlike arange where the beginning value was returned, the final value was not, the stop value was not returned. Here, both endpoints are being returned, but you can actually use an argument which will change matters. So here, what you're asking for is start at 3, end at 10, but do not include the endpoint. And since you have not specified the number of elements your array should have, it's going to default at 50. But now, it's going to be 50 intervals. And so the gap is 7 by 50, 0.14. And there's one more argument which is quite useful given the fact that figuring out exactly what the step is going to be can often be rather difficult. It's called ret step. Its default value is true, default value of ret step is false, just like the default value of endpoint was true. But if you say ret step equal to true, what Python does is that it actually returns to you two things in a tuple. So it produces a tuple, as you can see from this bracket around this. And there are two elements in tuple. The first element is the array that you have all been seeing so far. The next element, of course, is a step. So that's what ret step does, returns the step as well. Very often, you would want to get both of them. Of course, the function returns them in a tuple because it has to return a single number or single object. All Python functions return a single object. So because here you want to return several things, it's returning a tuple. But it would be actually useful if you could perhaps break this up into two pieces. And that's easily done by using unpacking. So here on the left hand side you have two variable names, capital A and H. And because Linspace is returning a two element tuple, the first element of the tuple goes into capital A, the next element goes into H. So you manage to get both in one go. A. By the way, there's a neat trick which you might often use if you did not really want H, just wanted A, and your function returned two things. You could use an underscore in place of the thing that you don't want. So this way, Python still has two things to unpack into, but the underscore essentially tells Python just throw away the value. So here, of course, all you get is A. Now, as you must have realized, there is no reason to use the underscore here because you could just as well have just omitted the ret step equal to true argument and you would have got exactly this. However, there are many situations in Python where a function is designed to give you several outputs in a tuple and you may want only one or two of them. So you just put in variable names in the places where you want and put underscores for the variables you don't want. You will throw away those other things. We also have one more function which can be used to create an array of equally spaced numbers, but this is a slightly different kind of equal spacing. It is not equal spacing on equal intervals, it's equal spacing on the log scale. And the name of the function is logspace. So np.logspace followed by three arguments. One of them is the starting value, the next one is the ending value, and next is the number of points. If you look at the array A that's been created now, notice that it has started at a value which is 100. Now what has that got to do with the arguments I gave here? 2 is the power to which the base, which by default is 10, is raised to. This is 10 to the 2 where you start, 10 to the 5 where you stop, and in between there are 10 equally spaced numbers, equally spaced on the logarithmic scale. So these numbers are actually in geometric proportion to each other. The base by default is 10, but I can actually change the base. For example, I can use the keyword argument base to change it to say 2. So now I have equally logarithmically spaced numbers, 10 of them starting at 2 to the power 2, ending at 2 to the 5, and this is what A looks like. So 2 to the 2, 4 is where it starts, 2 to the 5 is where it ends. There are 9 intervals, so 2 to the power 3, which is 5 minus 2, by 9, that's 2 to the 1/3, is a common ratio, and that is why, for example, after 3 steps, the initial number gets multiplied by 2. And then again, cube root of 2 times 8, cube root of 2 times that, and another cube root of 2 gets 16, and so on. And just like in log space, here the endpoint, just like in Linspace, the endpoint is included by default. You can actually use endpoint equal to false is true by default in order that the endpoint not be included, in which case now you have 10 numbers which does not touch 2 to the 5. Okay. And as you must have noticed, with keyword arguments, it does not really matter what order you give them in, since you're naming the arguments anyway. Now, let's move on to some other functions which can create arrays. One such function which will be pretty useful once we start plotting graphs using matplotlib or doing other calculations on a grid is one which produces a grid. And for this, let's make use of the Linspace function that we have learned so far. Let's say we use x equals np.linspace. This is 0, 5, and we want 10 points, or maybe 5. And let's say y is another array. It starts at say minus 2, 2 plus 2 with again 10 points, or maybe let's make it 8 points. Just so that you don't think that you have to use the same number of points for both the arrays here. So x is an array which looks like this, y is an array which looks like this. Now the name x and y invokes the idea of Cartesian coordinates or points, and what we can think of is a lattice made with these x values and these y values, but then the x values and y values will have to be repeated over and over again, and for that you need a function called mesh grid. So if you form a mesh grid using the inputs x and y, it essentially produces coordinates of grids of points. All the x values are returned in one array, all the y values possible are returned in another array. So let's say, so these are two arrays which are returned in a tuple. So I unpack that into the two arrays x and y, and now notice x has these values which are basically the same array that you had in small x, this one, but repeated 8 times, 1, 2, 3, 4, 5, 6, 7, 8. As many times as there are y's, and y on the other hand, the same array that you had here, repeated 10 times, but not repeated actually down the columns. So x and y gives you the row column values or x and y coordinates of a bunch of points. Just to see an example of this in action, let's take a look at my presentation file. Example of the Linspace function coupled with the measure function in action. Here we have produced a linearly spaced array of 100 numbers starting at 0, ending at 10. A similar array with y. We have produced a mesh grid of xy. And now we have created another array which takes sine of the values of x times squares that and multiplies it by sine of the values of y. So basically we have a 100 by 100 array of points. In each point we have evaluated sine square x times sine y and stored the result in an array z. Now this is what happens when you use the 3D plotting capabilities of Matplotlib to plot this z as a function of x and y. We are going to describe Matplotlib 3D plotting later. For the time being, let me just leave you with what this simple thing is capable of. So notice that this is a 100 element array, this is a 100 element array. Capital X and capital Y are 100 by 100 element arrays each, and here Z produces a 10,000 element array corresponding to the X and the Y values. Okay. One more interesting way of creating an array is by using a Numpy function called from function. To see this in action, let us first define a function of two variables because we want to create a two-dimensional array for the time being. And let's say we want the function to return 10 times x plus y. That's it. Now, what we will do is something like this. We will create an array using the from function method that Numpy provides. And the arguments that you give from function is first the name of the function to be used and then the shape of the array which you want. Say, let's say I give 5, 5. So what from function will do is that it will produce an array, a 5 by 5 array, the shape that has been given here, and the values that it will put in the various positions are linked to the index values. So, for example, at the top left corner, you have the 0, 0 element, where both indices are 0. So the value that from function will put in that position is 10 into 0 plus 0. The next element, the 0, 1, 1, will have values 10 into 0 plus 1, and so on. So this is what the array A is going to look like. So here you can see that this is 0, 0 giving you 0, 0, 1 giving you 1, 0, 2 giving you 2, and so on. On the other hand, here you have 1, 0 giving you 10, 1, 1, 1, 2, 1, 3, and 1, 4, and so on. Notice these are really not 1, 4. This is 1 into 10 plus 4. This is 3 into 10 plus 4, and so on. One advantage of using this array would be when we want to make sure what's happening at different index locations. An array created like this using the 10 into x plus y function actually tells us at a glimpse which element is it that you're talking about. So if the 3, 1 element here is actually 31, 4, 2 element is 42, and so on. When we demonstrate slicing, etc. later, this is going to turn out to be quite a handy thing. That we have learned of several ways of producing arrays. In the next video, we are going to take a look at how to index and slice arrays, and also a lot of other nice things that you can do with arrays.